Okay, so for this video, we're going to be going through some chapter 2 examples. We're going to focus more on the math examples or any of the numerical examples that we may have had to rush through in class or that you want to look over again. So you can flip through your packet to find any of the questions. They should follow through in kind of chronological order. So we're starting here with the law of definite proportions. This question is asking us to prove that the results that are described here are consistent with the law of definite proportions. Okay, so we should see that the breakdown of the ratio of carbon to oxygen in each of the samples is the same for it to be consistent with the law of definite proportions. Okay, so I like to break it down by writing out my two samples, like writing out sample 1 information and writing out sample 2 information. And the first step, which is sometimes overlooked, I think, and maybe the most important step, is to organize your information for yourself so that you don't lose something in the transition from reading it to calculating it. Okay, so one sample is going to produce 25.6 grams of oxygen and 9.60 grams of carbon. The other sample is going to produce 21.6 grams of oxygen and 8.10 grams of carbon. Okay, so now we've written these down correctly. Now we can create a ratio, and we want to create the same ratio in both samples. Okay, when I mean the same ratio, I mean that we're dividing oxygen by carbon in both samples, or carbon by oxygen in both samples. But whatever the method that we're going to use, we have to make sure it's the same method in both samples. So we're going to take the mass of the oxygen, and I'm choosing the oxygen because it is a larger number, so it's going to give us something that's bigger than 1. That's how I like to set up these ratios when I have a choice. So we'll put the mass of the oxygen in both examples and we'll divide it by the mass of the carbon. When we do this process, if the samples are consistent with the law of definite proportions, when we do this division, we should get the same result for both of these samples. Okay? So here we have 25.6 grams divided by 9.60 grams. And we get 2.67. And what this means is that we have a ratio of 2.67 grams of oxygen to every 1 gram of carbon. Okay, and if we do the same thing for our second sample, we have 21, that's a 2. Okay, we do that division. We also get 2.67. So again, we have a 2.67 to 1 ratio between oxygen and carbon. Okay, our decimals match. So this checks out. This is consistent with the law of definite proportions. So we're going to look at another example of this. Okay, this was an example of carbon dioxide. Now we're going to look here at an example of carbon monoxide. And what we're going to see is that the numerical value of the ratio is going to change. But in both of these carbon monoxide samples, the ratios of sample 1 to sample 2, when we're talking about carbon monoxide, that number will be the same. Okay, but the actual ratio number, the 2.67, this is true for carbon dioxide. This value won't be true anymore for carbon monoxide. And that plays into the law of multiple proportions we'll talk about next. Okay, so again, for our step 1, we'll sort out our sample data. So here we have 17.2 grams of oxygen and 12.9 grams of carbon. And then sample 2, 10.5 grams of oxygen and 7.88 grams of carbon. Okay, so again, I'm going to take my oxygen mass and divide it by my carbon mass in both samples. (10.5) divided by 7.88 is also 1.33. So this checks out. And again, this is the law of definite proportions. Okay, and for these carbon monoxide samples, what we're saying is that for every 1.33 grams of oxygen, there's 1 gram of carbon. That's going to be the simplest breakdown in terms of oxygen mass to carbon mass for any sample of carbon monoxide that's present. Okay, so we have a conceptual question that comes up next. So let's take a look at this one. And this says, we just saw that well, we didn't actually see this. Must be in your textbook though. So we see here that the mass ratio of nitrogen to hydrogen in ammonia is 4.7 to 1. Okay, so we'll write that down. So nitrogen is going to be 4.7, hydrogen is going to be 1. If a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen does it contain? Okay, so this is the ratio that they gave us, 4.7 to 1. And what this means, again, is that for every 4.7 grams of nitrogen that's in a sample of ammonia, we're going to have 1 gram of hydrogen. Okay, we can use this just like a unit equation like we were working with in terms of conversions. Okay, so if I want to know how many grams of nitrogen there are in 10 grams of hydrogen, I can use my unit equation to figure this out, because I know that for every 1 gram of hydrogen, I'm going to need 4.7 grams of nitrogen. Okay, so that means that there are going to be 47 grams of nitrogen present if I have 10 grams of hydrogen in a sample of ammonia. And the formula for ammonia, in case that's not familiar to you yet, is NH3. Okay? Now let's take a look at how we would use some of this information to kind of figure out whether samples are consistent with the law of multiple proportions instead of the law of definite proportions. So here they're telling us that nitrogen forms several compounds with oxygen, including nitrogen dioxide, which means 1 nitrogen and 2 oxygens, and dinitrogen monoxide, which is 2 nitrogens and 1 oxygen. Nitrogen dioxide contains 2.28 grams of oxygen for every 1 gram of nitrogen. And dinitrogen monoxide is 0.570 grams of nitrogen, or of oxygen rather, sorry, for every 1 gram of nitrogen. We want to show that these results are consistent with the law of multiple proportions. So the law of multiple proportions is that law that said something like, if you have element A and B, if you look at the ratio of element A for every 1 gram of element B, the result of that ratio will be a small whole number. That's what we're going to prove. That's what we're going to prove right here. Okay. So when you're looking at the law of multiple proportions, we're looking at two different compounds. Okay, so we should write that down there. So it's two different compounds with the same elements. Okay, so in this case, NO2 and N2O are two different compounds, right? They have different amounts of nitrogen and oxygen in each one, but they're both made up of the same elements, right? So what we're going to do is, you see we have both of these ratios are set so that they're comparing the oxygen amount to 1 gram of nitrogen. So what we're going to do to figure out if these compounds are consistent with the law of multiple proportions, so we're going to focus in on these values that are not 1. So we're going to focus in on that other element that makes up the compound. So we're going to take the bigger of the two values and divide it by the smaller and see if we get a whole number back out. So we're going to take 2.28 grams of oxygen and divide it by 0.570 grams of oxygen. And if this is consistent with the law of multiple proportions, we'll get a small whole number when we do this division. Okay, and here we get 4. So that checks out. That is consistent with the law of multiple proportions. Okay, let's try one more. Okay, just take a peek at that one. Take a minute to write down your information. Okay. So these are our sample breakdowns. So now from here, I'm going to focus in on the hydrogen because the hydrogen is not 0. And I'm going to divide the bigger one by the smaller one. Okay, and I get 2. So that is a small whole number. That is consistent with the law of multiple proportions. Yeah, so let's take a look at this question and talk it out. Which statement best captures one of the differences between the law of definite proportions and the law of multiple proportions? Okay, now take a second to actually read this and try to figure it out for yourself before you see the answer come up. Choice A says the law of definite proportions. Let me just write them both down here. Definite proportions versus multiple. The law of definite proportions applies to 2 or more samples of the same compound. The law of multiple proportions applies to 2 different compounds with the same elements. Choice B says the law of definite proportion applies to 2 different compounds containing the same elements, and multiple proportions applies to 2 or more samples of the same compound. Then choice C says none of the above. They both apply to multiple samples of the same compound. All right, so again, I'm going to write this down here. Same compound. We could say that they're different samples, but they're the same compound. Okay, and we could say that an example would be H2O sample 1, H2O sample 2. Okay, the law of multiple proportions, we're going to be looking at different compounds, but the same elements. Okay, and examples would be H2O versus H2O2, for example. We could even put a little versus here. Okay, so this is going to be the difference between these two laws. All right, let's try this one. This one moves us into our discussion of what makes up an atom. And we'll have a few of these questions coming up. What are the atomic number, mass number, and symbol of a chlorine isotope with 18 neutrons? Okay, we have to remember what each of these terms means. Very important that you know what these terms mean. You don't want to just be guessing on your exam. Okay, when we say the atomic number, and the atomic number has the symbol Z, right? The atomic number is going to be equivalent to the number of protons. Okay, we can find this number directly from the periodic table. And in the case of chlorine, the Z value is 17. Okay, this means that chlorine has 17 protons. It also means that in a neutral chlorine atom, there would be 17 electrons. All right. The mass number, which is represented by a big A, the mass number is going to be the sum of all of the protons and neutrons in a nucleus. Okay, and the mass number is not the same thing as the atomic mass. They're very similar values, but they are not the same thing. The atomic mass is going to be the mass value, the average mass value, taking into account the natural abundance of all the different isotopes of your elements. The mass number is going to be the sum of the protons and neutrons in the nucleus of a specific isotope. Okay, so in this case, they told us that we have chlorine with 18 neutrons. That means that our mass number for this isotope is going to be 17 plus 18, my protons plus my neutrons. So my mass number is going to be 35. To write out the isotope symbol for any element, your mass number goes on top, so the bigger number goes on top. Your number of protons goes underneath it. And then you write the chemical symbol of the element next to it. Okay. So let's try this out we want to know how many protons, electrons, and neutrons are present in 52 Cr. Okay, so we're going to just pull apart the symbol that we see here. So right away, we know that this here is the atomic number. So that's going to equal the number of protons. We see that the chromium is neutral here And we can tell that it's neutral because there's no charge indicated. If there were a charge, we would find it up here in this top right corner. But there is no charge there, and that means that the chromium is neutral. Something that's neutral has the same number of positive and negative charges. Okay, so if I have 24 protons in my neutral chromium, that means that I have 24 electrons as well. Okay, now to find out the number of neutrons that are present, I'm going to use my mass number. So my mass number is my protons plus my neutrons. So if I take my mass number of 52 and I subtract my protons from that, I'm going to find the number of neutrons present. Okay, so I have 24 protons, 24 electrons, and 28 neutrons in the chromium 52. Okay, let's take a look at the next conceptual connection question. Here we're asked, or we're told that an argon isotope has a mass number of 40. So the A value is going to be 40. How many neutrons does it contain? If we look up argon on the periodic table, we see that the atomic number is 18. So to find the neutrons, it's going to be your mass number value minus your proton value, A minus Z, or 40 minus 18. So we'll have 22 neutrons. I'll make that a little bit bigger. Now let's try this one out. This one's a good one. This question says, how many electrons are present in the O2 minus anion? Okay, so we'll start by writing out the symbol for the oxygen anion. Okay, so when you're trying to figure out how many electrons are present, you have to look at the relationship between the protons and the electrons in any of the ions that you're looking at. Okay, we know based on the fact that the chemical symbol is O, we know right away how many protons are present. Okay, that is not changeable. All oxygen is going to have, all oxygen isotopes, neutral atoms, ions, all oxygens are going to have 8 protons. Okay, every proton has a positive charge. So if my oxygen ion has a -2 charge and it must have 8 protons, that means it has to have 2 electrons more than the protons it has. Okay, so if a neutral oxygen, we'll say neutral O, has 8 protons and 8 electrons, then one with a -2 charge must have 8 protons and 10 electrons. Right? We can never change the number of protons that are present. If we change the number of protons, we're changing the identity of the element. But we can change the number of electrons, which will change the charge value associated with the atom or ion. Okay, so this next question is asking us to look at our periodic table and to predict the charges of the ions that would be formed by the main group elements here. Okay, so we have aluminum, sulfur, nitrogen, and rubidium. So the first thing to do is to go through each of these examples or each of these elements and to determine whether it's a metal or a nonmetal. Okay, and that's because your metals are all going to have a positive charge and your nonmetals are going to have a negative charge. All right, so when you're going through and one of your first decisions has to be whether you have a plus or minus charge. Okay, you can make that easy for yourself by using the periodic table and literally just going through and looking. Okay, I'm sure you have nicer versions of your periodic table with you so that you don't have to try to look at mine and see what it's looking like here. But we're focused in on aluminum, sulfur, nitrogen, and rubidium here. Okay, so remember, we have that line here that's going to separate our metals and our nonmetals. So everything up in this corner, these are all nonmetals. Everything else in this periodic table is going to be some version of a metal. Okay, so aluminum is a metal. Okay, sulfur is over here and nitrogen is over here. These are both nonmetals. And rubidium over here in group 1 is a metal. Okay, so we know right away that we're going to have a plus charge here, a minus charge here, a minus charge here, and a plus charge here. Now, your main group elements are always trying to form ions that will get them to have the same valence as the nearest noble gas. Okay. And we're going to look at the periodic table for us to figure out like what I'm talking about here. So you have to remember where the noble gases are on your periodic table for this to kind of make sense. So your noble gases are over here in this last column. So if we have something like aluminum, we already know that it's a metal. Okay, it's in group 3. Remember, that's how we number our main groups. This is group 1. I know this is dark on dark, so it's harder to see, but I think you guys can follow along. Right, these are the numbering system of our main groups. So aluminum is in group 3. Okay, it's a metal, meaning that it has 3 valence electrons. So it's going to lose its 3 valence electrons so that it can have a noble valence structure like its nearest noble gas, which is neon. All right, that's the nice thing about metals is that the ions that they form, main group metals anyway, the charges on them correspond to their group number. Okay, so aluminum is going to have a +3 charge when it forms an ion. Rubidium, which is in group 1, is going to have a +1 charge. Your nonmetals, and again, we're focusing in on the sulfur and the nitrogen here, they have to gain electrons in order to fill their valence shell. So they're going to gain as many electrons as they need to mimic their nearest noble gas. So nitrogen is going to try to add electrons to its valence until it has as many electrons as neon. And specifically, it's going to, if it's in group 5, it needs to add 1, 2, 3. Sulfur needs to add 2 electrons, 1, 2. As many electrons as they add, that's as much negative charge as they're picking up. So sulfur has to gain 2 electrons. Its charge will be -2. Nitrogen has to gain 3 electrons. Its charge will be -3. Okay. The next question we're going to look at has to do with isotope abundance. We're going to do a few examples of this where we are calculating atomic masses based on isotope percentages and isotope masses. So I'm going to write down the formula first. This will be the formula that we'll refer back to. Okay. So when we're looking at the isotope abundances and their corresponding isotope masses, and we want to find the atomic mass from those values, we end up with this relationship here. This looks a little bit different than how your textbook writes it out, but it means the same thing. To find the atomic mass, we're going to take the fractional abundance of isotope 1, multiply it by the mass of that isotope. We're going to take the fractional abundance of isotope 2, multiply it by the mass of isotope 2. If there are more isotopes, we would repeat that process for every isotope that's available. And then at the end, we're going to add together all of these values. And when we add those values together, what we end up with is the atomic mass. Okay, so the question that we were given here is that naturally occurring chlorine consists of 75.77% Cl35, which has a mass of 34.97 AMU, and 24.23% Cl37, which has a mass of 36.97 AMU. Okay, so the way this works right off the bat, what you'll be able to tell about the overall atomic mass of chlorine is that because 75% of chlorine exists as Cl35, the overall atomic mass of chlorine is going to be closer to this value than to this value, because these percentages make a difference in what the overall atomic mass value ends up being. Okay, now to put this information into our formula, we need to do one thing first. We need to take this percentage value and we're going to convert it into a fractional abundance instead of a percentage. And it's very easy to do this. We're just going to take our percentage and we're going to divide it by 100. And we'll do the same thing for our chlorine 37. Okay. Once we have those, we're going to go through this process that I talked about. We'll take the fractional abundance of isotope 1 and we'll multiply it by the mass of isotope 1. Okay, so we have 0.7577 times 34.97 AMU. And then the fractional abundance of isotope 2 times the mass of isotope 2. Okay, so we do this multiplication and we get 26.4968 AMU plus 8.9578 AMU. Okay, now we're going to add these two values together. And we end up with an atomic mass. I can write that out front. I could have been writing AM over here, just so we don't forget what we're calculating. 35.45 AMU. And if you look on the periodic table, that is the atomic mass of chlorine. Okay, so let's take a look at another example. And again, I would recommend that kind of at this point that you pause the video and you try this on your own. And then you, only after you try it out on your own, watch me work it out so that you are actually trying to do it. And you're not just watching me do it. It's not going to help you on your test, right? So let's write down this information. Okay, so after we get our information written down, the first thing that we want to do again is to take these percentage values and right away convert them into fractional abundances. So this will be 0.6917 because I'm dividing that by 100. And this will be 0.3083. Now that I have my fractional abundance values, I can calculate my atomic mass. I'll start by taking my fractional abundance of copper 63 and multiplying it by the mass of copper 63. And then we have the fractional abundance of copper 65 times the mass of copper 65. Okay, so we have 43.5353 AMU plus 20.0172 AMU. Try to keep track of the sig figs as much as I can. And then we're going to add these values together. We end up with 63.55 AMU as the atomic mass. And again, if you looked at the atomic mass of copper on the periodic table, that is what you would find. Right? So that means that we did a good job there. Okay, let's look up our next example. In this case, we have magnesium, which has 3 isotopes. We'll see that the process for solving for 3 isotopes isn't any different really than solving for 2 with just 1 extra step. We'll write down our values here: 23.99 AMU, 24.99 AMU, and 25.98 AMU. Okay. So I'm just going to show you another way that you could set up your solving. So these are the masses. This is isotope 1, isotope 2, and isotope 3 of magnesium. I'm going to take the isotope mass, I'm going to multiply it by its corresponding fractional abundance. So the first isotope has a percentage of 78.99%, which means that the fractional abundance is 0.7899. The second isotope has a natural abundance of 10%, which means that its fractional abundance is 0.1000. And the third isotope has a fractional abundance of 0.1101. So I can take the mass values and multiply them by the fractional abundance. And write out the corresponding values this way. Okay, and when I get these values, I'm going to add them together. Okay, that's why sometimes I like this setup a little bit better, because I end up with just the sum column over here. Personal preference. Either setup will work just fine. Okay, and we end up, oh, I messed that one up, sorry. It's 2.8604. We end up with 24.31. Okay, the next example has one that's a little more interesting. So this will be fun. Okay, so in this case, they're telling us, oh, this one. In this case, they're telling us that gallium has 2 naturally occurring isotopes. Okay. Gallium 69 and gallium 71. And they're telling us that gallium 69 has a mass of 68.9256 AMU and a natural abundance of 60.11%. And they want us to use the atomic mass of gallium from the periodic table, which if we look gallium up on the periodic table, it's 69.723 AMU. And they want us to use this information here to find what the mass value is of this isotope. Okay, so we're going to use the same formula that we've been using. It's just that we have slightly different information to start with. Okay, we still have a percentage here, which we can turn into a fractional abundance, 0.6011. We're missing the mass here, so we have some question marks here for the mass of this isotope. And we were not told the percentage of this isotope explicitly, okay? But we can figure this out. They did not tell us what the percentage of gallium 71 is, but they told us that there's only 2 isotopes, okay? If we have 2 isotopes, then the percent of isotope 1 plus the percent of isotope 2, what do these have to equal? When you add percent 1 and percent 2 together, they have to equal 100%. So if I know that isotope 1 is 60.11%, and I know that it has to add up to 100%, I can subtract 60.11 from 100, and that'll tell me what the percentage of my other isotope is. So my isotope 2% is going to be 39.89%. And I can turn that into a fractional abundance of 0.3989. Okay. Now I have enough information to solve this, because I'm just going to plug all this information into my formula that I wrote out up here. Okay, my atomic mass, that's the mass that I pull from my periodic table. So that's going to be 69.723 AMU. And that's going to equal the fractional abundance of isotope 1, which is 0.6011, times the mass of isotope 1, plus the fractional abundance of isotope 2, times the mass of isotope 2, which I don't know. I don't know it, so I'm going to call it X. Okay. So now this just becomes an algebra problem. I'm going to multiply this little set of parentheses out. I'm going to keep some extra decimals until the end. And over here, this turns into 0.3989x. Okay, so now I'm going to isolate this x term by subtracting the 41 from both sides. Okay, and I end up with 28.2918 AMU. That's going to equal 0.3989x. And remember that x value, that's the mass of that gallium 71 that I'm looking for. So to solve for x now, I'm just going to divide both sides by 0.3989. Okay, and we get 70.92 AMU equals x, and that's the mass of gallium 71. Okay, so it's the same formula. We just have to use it a little bit differently when we're asked that different question. Okay, so now we're going to switch gears a little bit. We have some calculations to do with grams, moles, and Avogadro's number. Okay, so our first question asks us what the number of copper atoms is in 2.45 moles of copper. Okay. When I'm setting up for dimensional analysis, and I recommend that you do this at the beginning, rewrite the question as a math problem for yourself, so that you're able to set up your units correctly, and you're able to cancel them out as you go and end up with the unit that you're looking for at the end of your calculation. So for example, here it's saying calculate the number of copper atoms in 2.45 moles of copper. So what it's asking are how many copper atoms equals 2.45 moles of copper. Okay, if I can set this part up correctly, then I'm well on my way to being able to set up my dimensional analysis correctly, because I know that I'm starting with the unit of moles and I want to convert that into the unit of atoms. Okay, and the relationship that I'm going to be able to use to do this is my Avogadro's number relationship, which says that 1 mole of anything equals 6.022 times 10 to the 23 of that thing. Okay, so if I have 1 mole of an atom, that's 6.022 times 10 to the 23 atoms. If I have 1 mole of molecules, that's this many molecules. If I have 1 mole of soccer balls, that's 6.022 times 10 to the 23 soccer balls. All right, so that's why I wrote it like this. 1 mole of anything is this many of that thing. So when I'm looking here at this this equation I've set up, I have 2.45 moles of copper. Well, I know based on Avogadro's number that in any 1 mole of copper that I'm going to have 6.022 times 10 to the 23 atoms of copper. Okay, so when I have an element, maybe I can write it like this. So 1 mole of an element is going to equal 6.022 times 10 to the 23 atoms of that element. One mole of a molecule or a compound means that there'll be 6.022 times 10 to the 23 molecules of that compound. Okay, so when I'm looking for the number of copper atoms and I have the number of moles, I can use this relationship to figure out how many copper atoms there are in this particular sample. And again, I'm using dimensional analysis. So everything that's on the top of my fraction bars, I'm going to multiply. So I'm going to do 2.45 times 6.022 times 10 to the 23. And it turns out that there are 1.48 times 10 to the 24 copper atoms in the sample that we're looking at. Okay. So let's look at another example. Here we're looking at kind of the reverse process. In this case, they're telling us that a silver ring contains a certain number of silver atoms, and we want to know how many moles of silver atoms that equals. I'm just going to rewrite Avogadro's number up here. Because this is the version of Avogadro's number that we're kind of using in these examples when we're looking at particular elements. So here we want to know how many moles of silver atoms there are in 2.80 times 10 to the 22 silver atoms. Okay. Now, again, we're looking for this relationship between atoms and moles. This relationship between atoms and moles comes back to Avogadro's number. In this case, we know the number of atoms and we want to convert it into moles. So atoms is going to go on the bottom of our fraction bar and moles is going to go on the top. And we're going to look back at our unit equation to figure out the numbers that go here. The 1 is still attached to the mole. So in every 1 mole, there are 6.022 times 10 to the 23 atoms. So our atoms will cancel out. And we end up mathematically, if we put this over 1, taking 2.80 times 10 to the 22 and dividing it by 6.022 times 10 to the 23. And we should end up with 0.0465 moles of silver. Okay. Now we're going to take this one step further because we're going between atoms and moles and moles and atoms. But we can use mass values and convert those between, like convert mass into atoms or atoms into a mass value. And it just involves one extra step. So in this case, we're assuming that pencil lead is made out of pure graphite, which is a form of carbon. Calculate the amount of carbon in atoms contained in 0.0265 grams of pencil lead. Okay. So we have 0.265 grams of carbon. All right. Now, the relationship that we've been using so far, let me actually rewrite this the way that I was just telling you guys, because we want to know how many atoms there are in 0.265 grams of carbon. We're starting with grams here, and we want to convert this into atoms. Okay. The only conversion that we know that will get us into atoms is a conversion between moles and atoms. So we can't go directly from this value into atoms. We have to go, there has to be another go-between for us. And to get from any mass value of an element into its corresponding mole value, we're going to use the periodic table for that and the atomic mass of our element on the periodic table to do that. So if you look up carbon on the periodic table, you'll see that it says 12.01 for the atomic mass value. What that means when you have the your atomic masses, you'll see them written out like this, 12.01 AMU. Okay, and this is an atomic mass unit. Another unit that you can use to look at the atomic masses in your periodic table is grams per mole. Okay, and the numbers that are associated with these two units, they're equivalent. Okay, so 12.01 AMU or 12.01 grams per mole. Those numbers on the periodic table, you can use either of these units for those numbers. And what this number means in particular, we call this the molar mass. When we look at the molar mass, we can represent this as the unit equation. We can say that for every 12.01 grams of carbon, that equals 1 mole of carbon. Okay, and if we do this, if we have this relationship, now we have a way to go from the mass value of carbon into a mole value of carbon. Okay, once we have a mole value of carbon, then we can use Avogadro's number and figure out how many atoms of carbon are present. So what I like to do for questions like this is I like to rewrite my molar mass as another unit equation underneath Avogadro's number. So for every 1 mole of carbon, I know that there are 12.01 grams of carbon. Okay, so now when I'm looking at this mass value for carbon, I see how I can get out of grams and I can convert it into moles. I'm going to put my unit of grams on the bottom of my fraction bar so it cancels out, and moles up top. So in every, well, it's mole up top. In every 1 mole, there's 12.01 grams. And now my unit of grams is canceled out. Now I want to convert into atoms. Well, now that I'm in moles, now I can convert into atoms. In every 1 mole, which will cancel out now, there is 6.022 times 10 to the 23 atoms. Okay, so what we end up doing mathematically here is multiplying everything that's on the top of the fraction bar and dividing by everything that's on the bottom of the fraction bar. So 0.0265 times 6.022 times 10 to the 23 divided by 12.01. Okay, and we should end up with 1.33 times 10 to the 21 carbon atoms in this sample. All right. Now we're going to look at a different example where we're going to start with, this one's a little bit easier because we're starting with a mass value for copper, and we want to calculate how many moles of copper there are. So if you're ever wondering, like, how do I know whether I need to do 1 conversion or 2 conversions? You need to ask yourself, is there a way for me to go directly from the unit that I'm given to the unit that I'm looking for? Okay. Looking at copper here. And just rewrite this so that it's for copper instead. This value is from the periodic table, 63.55 grams per copper per mole. Now, when you're asking yourself, does this need 1 conversion factor or 2 conversion factors? You have to look at these unit equations that you know and say, well, is there one that goes directly from grams to moles? If there's one that goes directly from this to this, then you only need 1 step. And in this case, the molar mass does that. Because I can look at the molar mass and say, well, I'm going to put grams on the bottom here. 63.55 grams is in 1 mole of copper. So if I take this mass value and divide it by 63.55, I'm going to have a copper value that's in terms of moles. Okay. This next question looks at the reverse process. Here we're looking at titanium. We're asked to calculate the mass of titanium in grams of 0.473 moles of titanium. Okay, so if you look up titanium on the periodic table, we see that it's 47.87 grams per mole, which means that every 1 mole of Ti is going to have 47.87 grams. Okay, so we're starting with moles up on the top of our fraction bar. So we know we want to put it, that same unit down here so that it cancels out. And then we're going to use the mole to gram conversion here from our molar mass. Okay, so we have 0.473 moles times 47.87. And we end up with 22.6 grams of titanium in this sample. Oh, sorry, I was supposed to share that with you guys. I'll give you a second to look at that now. I forgot to take off that share screen. Okay, this next question's a good one. Because this next question goes, asks us to assume that pennies are made of pure copper. How many copper atoms are in a copper penny with a mass of 3.10 grams? So we're going from a gram value into copper atoms. Okay, so now we're going to need both of our conversions here. And again, the reason that we know that we need both conversions is because there is no direct conversion from grams to atoms, right? We can do grams to moles with the periodic table, and we can do moles to atoms with Avogadro's number, but we can't go from grams to atoms directly. All right. So when we look up copper in the periodic table, the molar mass is 63.55 AMU, which means that for every 1 mole, there's going to be 63.55 grams. Separate out all this information with these lines. So we want to know how many Cu atoms are there in a copper penny with a mass of 3.10 grams. Okay, so my first step is going to be to put this unit of grams on the bottom of my next conversion so that this grams unit cancels out. Okay, I'm going to have to look at my molar mass conversion because this is where I have grams converting into something else. So I can take grams and I can turn it into moles. In every 1 mole, there's 63.55 grams. Okay, now that I have the information in terms of moles, now I can go up to Avogadro's number, which tells me that every 1 mole has this many atoms. So this will be 3.10 divided by 63.55, because it's on the bottom of the fraction bar, times 6.022 times 10 to the 23. And I end up with 2.94 times 10 to the 22 copper atoms. Okay, let's take a look at a different one. This one's interesting because it throws a different type of conversion in to the mix. And this can happen. I mean, in this case, they're just giving you another unit equation for you to use. So they're saying that you have a 1.3 carat diamond and you want to know how many carbon atoms there are in a 1.3 carat diamond. Okay, so like this is going to be your overall question. Okay, and they give you the conversion factor between carats and grams right here. And as you can imagine, that's going to be important. Okay, I know that if I am trying to end up with a number that's in atoms, I'm going to need Avogadro's number here. So I'm going to write out, I know that I'm going to need this relationship, that 1 mole of carbon is going to be 6.022 times 10 to the 23 carbon atoms. I know that from the information they gave me in the problem that every 1 carat is equal to 0.20 grams. And I also know how to get between grams and moles because I can do that from my periodic table. If I look up my periodic table for carbon, the molar mass is 12.01 grams per mole. So I know that for every 1 mole of carbon, they're going to be 12.01 grams of carbon. And I can use all 3 of these conversion factors to get from carats into atoms. Okay, just one step at a time. So the first thing I want to do is I want to get rid of this unit of carats, right? So I'm going to put carats on the bottom. I'm going to put grams on the top because I want to get rid of carats and turn it into grams. I'm going to look at this conversion factor that they gave us here. So every 1 carat is 0.20 grams. Okay. Now I can look at my molar mass for carbon and go from grams into moles. Grams will go on the bottom so that I can cancel it out. Moles will go up top. So in every 1 mole, I've got 12.01 grams. Okay, now that I have my numbers converted into units of moles, now I can use Avogadro's number, which says that every 1 mole is 6.022 times 10 to the 23 atoms. Okay, and I'm going to multiply everything that's on the top, and I'm going to divide by everything that's on the bottom. And I would really take the time to attempt this so that you know that you're plugging it into your calculator correctly. Okay, you should end up with 1.3 times 10 to the 22 carbon atoms. All right, our next question asks us to calculate the mass of a certain number of tungsten atoms. Okay, so I'm going to rewrite our relationships up here. Tungsten has the chemical symbol of W on your periodic table. You should be becoming familiar with these chemical symbols of these elements so that you're not wasting your time on the exam trying to figure out what the symbol for a particular element is. So you should just know it offhand. So every 1 mole of tungsten is going to be 6.022 times 10 to the 23 tungsten atoms. And the molar mass of tungsten is 183.84 grams per mole. So every 1 mole of tungsten is going to equal 183.84 grams. Okay. So with that, we can write out our question. How many? It just says, what is the mass of it? So we'll assume that they mean the mass in grams. If they wanted a different mass value, they would have indicated that in the question itself. So how many grams of tungsten equals 2.25 times 10 to the 22 tungsten atoms? Okay, so in this case, we know that we're going to put the atoms on the bottom. And we're going to put moles on the top because that's the conversion that we know that uses atoms. We are going between atoms and moles. In this case, because we started with atoms, we have to put Avogadro's number on the bottom of our conversion so that we're converting out of atoms and into moles. Okay. Once we've converted into moles, then we can use our molar mass, which says that every 1 mole of tungsten is going to be 183.84 grams. So here we'll have 2.25 times 10 to the positive 22 divided by 6.022 times 10 to the 23 multiplied by 183.84. We should end up with 6.87 grams of tungsten. Okay. Now we're going to get a little even more in depth here. A little more, I don't know if in depth is the right word. Get a little more complicated. Okay. I'm going to take it up a notch. So now we're going to be given information about a particular sample in terms of its atoms and its shape. Okay. So we're told here that we have an aluminum sphere and that the sphere has 8.55 times 10 to the 22 aluminum atoms in it. And we want to know what the radius of the sphere is in terms of centimeters. So I'm going to write that down as question mark centimeters. And they're also telling us that the density of aluminum is 2.70 grams per cubic centimeter. So with this information, we need to figure out what the radius of our sphere is. Okay. One other piece of information that's going to be helpful is knowing the volume formula for a sphere, which is 4/3 pi r cubed. Okay. So basically, we need to use this formula. I need to isolate this radius value. Because if the volume of a sphere is 4/3 pi r cubed, well, we want to know what that radius value is. Okay. In order to find the radius value, first we're going to need to figure out what the volume of the sphere is. All right, but luckily we were given the density value of aluminum. And density, remember, equals mass divided by volume. So if we know the density of aluminum, which we do, and we know the mass of aluminum, which we can find out from this, we can figure out what that volume of aluminum is. Okay. I'm going to solve out this density equation for volume real quick. So density equals mass over volume. So if I want to isolate this volume value, I'm going to multiply both sides by V. So V times D equals mass divided by D divided by D. So the volume of our aluminum is going to equal the mass of aluminum over the density of aluminum. All right. Well, how do we find the mass of aluminum? We've been doing that for the last few problems, right? They gave us the number of atoms of aluminum. 8.55 times 10 to the 22 atoms. So we want to take this atoms value and we want to go from atoms of aluminum into moles of aluminum, and from moles of aluminum into grams of aluminum. And once we know the grams of aluminum, we're going to pop it right in there. Okay, and we have this value here, which we'll put right there. Sound good? Okay, so we're starting with atoms here, up top. So we know that atoms is going to go on the bottom of our fraction bar so that it cancels out. And we know that Avogadro's number is going to go along with my unit of atoms. And up top will be 1 mole. Notice that in our conversion factor, it's always 1 mole. Even when we go to the next step, when we're looking to convert moles of aluminum into grams of aluminum, we look at our molar mass, which for aluminum is 26.98 grams per mole. It's grams per 1 mole. So 1 mole of aluminum has 26.98 grams. Okay, so let's get a little value here for our mass of aluminum. Okay, so we end up with a mass value of aluminum of 3.8306 grams. Okay. Now that I have this mass value for aluminum, now I can do my next step. The volume of aluminum is going to be the mass of aluminum divided by the density. So that's going to be 3.8306 grams divided by 2.70 grams per cubic centimeter. And that's going to be 1.4187 cubic centimeters. Okay, so this is the volume of my sphere. That's the volume of the aluminum I have. And I know it's in a spherical shape, so the volume of my sphere has to be this value. So now this volume value, I know that because it's in the shape of a sphere, it's going to be equal to 4/3 pi r cubed. Okay, so I want to isolate my radius value. That means that I'm going to, I have this underlined for sig figs. I am going to move these terms to the other side by multiplying by the inverse. So I'm going to multiply this side by 3 divided by 4 pi. I'm going to multiply this side by 3 divided by 4 pi. Okay. And remember when you're putting this into your calculator, it's 1.4187 times 3 divided by 4 divided by pi. Okay, when you do that, you should end up with 0.3387 centimeters cubed equals r cubed. Okay, and we're still to the that third sig fig there. Okay, if you don't get this value, you have to go back and plug this stuff back in. All right, now we have to take the cube root of this. In my calculator, when I take the cube root, I hit the second key and then I hit the y to the x, because up top that's where it switches into the cube root up there. So a second y to the x and then the cube root because it's the third. And that will give you the cube root of it. Or you can raise this number to the 1/3, and that's the same thing as taking the cube root. I did put calculator videos on the Blackboard site for each of the TI-30 calculators that we use in the class. So you can go back and check the calculator videos if you're not sure how to take the cube root on your calculator. But when you take the cube root of this number, you end up with 0.697 centimeters, and that is the radius value. Okay, so let's try this one. Same type of question. We have a titanium cube that contains X amount of atoms. What is the edge length of a cube if the density of titanium is 4.50 grams per cubic centimeter? So again, here we need to know a few pieces of information. First, the volume of the cube is going to be the edge length, which we'll call L cubed. Okay, so if we can find the volume of the cube, we'll be able to figure out what the edge length is. To find the volume of the cube, we're going to use the density of titanium, the same way we did before. The density of titanium is 4.50 grams per cubic centimeter. Density is also mass over volume, which we can solve for volume. And when we do that, we end up with volume equal to mass over density. So we need to know what the mass value is before we can figure out what the volume is. And we're going to find the mass value by using the number of titanium atoms. So that's 2.86 times 10 to the 23 atoms. Okay, so we want to convert out of atoms into moles. So atoms will go on the bottom and 1 mole will go on top. I always like to start with my units and fill in the numbers later, just to really reiterate that you should be placing your units based on the whatever unit came before so that everything cancels out. Now for this next conversion, I'm going to be going from moles into grams, and I'm going to use my periodic table to figure out what this gram value is. The molar mass for titanium is 47.87 grams per mole. Okay, we should get 22.73 grams of titanium. Now that we have that mass value, we can find the volume of the cube by taking the mass value and dividing it by the density. Okay, now that we have the volume, we know that that's going to be equal to the edge length cubed. So at this point, if we take the cube root of the volume, we are going to get the edge length. So the cube root of 5.052 is 1.72 centimeters. And that is the distance of the edge length of the cube that we're looking at here. Okay. The next example is interesting because we're going to be going in a different direction with our calculations. So this question is giving us the length and radius of a cylinder and the density of copper. And we're going to use that information to find the number of copper atoms that are present. I know, I'm like, this is interesting. You guys are probably like, this is terrible. I mean, it is kind of interesting though. Think that you could do this for anything as long as you have a little bit of information. I think it's kind of interesting. All right, I gotta write down this information. So we have a cylinder that has a length of 9.85 centimeters, radius of 1.05 centimeters, and the density of copper is going to be 8.96 grams per centimeter cubed. Okay, so we're just looking at like the reverse process here. So we can use this information to find the volume of the cylinder, right? And the volume of the cylinder is going to be equivalent to the volume of your copper. Once we know we have the density of the copper, right? And we know that density equals mass over volume. So that means that we can find the mass of the copper by taking our density and multiplying it by the volume. So we already have the density value. Once we have the volume value, we'll be able to find the mass. Once we have the mass of the copper, we can convert it into moles. And from moles, we can convert it into atoms. So that's our plan of attack here. So we'll start by finding the volume of the cylinder. They tell us that the volume of the cylinder is pi r squared times height or length. So we'll call it length here because that's the wording of the question. So pi times 1.05 centimeters squared times 9.85 centimeters. So you see in the end, we'll have cubic centimeters as our units. 1.05 squared times 9.85 times pi. All right, so our volume is going to be 34.117 cubic centimeters. Okay, so now we're going to use this relationship here that we talked about. The mass of our copper is going to be the density of the copper, which is 8.96 grams per cubic centimeter, times the volume. And we get 305.68 grams of copper. Again, it's to the 3 sig figs. And now this is the value that I'm going to use to figure out how many copper atoms I have. Okay, so I have 305.68 grams of copper. If I look on my periodic table, I know that I can go from grams of copper to moles of copper. There's 63.55 grams of copper in 1 mole of copper. And then I'm going to go from moles into atoms using Avogadro's number. There's 6.022 times 10 to the 23 atoms. Okay, and I'm going to round my final answer to 3 significant figures. So that will be 2.90 times 10 to the 24 copper atoms. Let's get that all in kind of in one frame. Okay, and you see how your units, they cancel out because all of the same units are on opposite sides of the fraction bar. We multiply everything that's on top of the fraction bar, divide by everything that's on the bottom of the fraction bar. All right. Let's look at the next one. For some of the next ones, I incorporated some other conversion factors into the questions just so we can remind ourselves of what those like more difficult conversion factors were, or the ones that you weren't used to. They're not really difficult, they're just not usual. So there's a question like this where it says, calculate the mass in ounces of 1.95 times 10 to the 21 antimony atoms. Okay, the mass in ounces. I'm gonna just write this down. 1.95 times 10 to the 21. Antimony is SB. Again, something that you have to know. All right. So what I would recommend doing here is making yourself like a roadmap of how you want to solve this problem. They gave us the number of atoms. Okay, and hopefully by now you feel comfortable recognizing that if you have the number of atoms of something, you can use Avogadro's number and you can find the moles of that thing. Okay, so we'll put a little note here that says Avogadro's number because that's what you can use to go from atoms into moles, right? Once you have the number in terms of moles, you can use your periodic table and you can look up antimony and you can convert it from moles into grams. Okay. And once we have this information in terms of grams, now you can go back to the table from your textbook In your textbook, it's table 1.3, this particular one. And this is the conversions that go from like your English units to your metric units and back, back and forth between those. There's a conversion on the table you have to have memorized for your exam between grams and ounces. Okay. You can use that conversion to get this value into ounces. Table 1.3 says that every 1 ounce is equal to 28.35 grams. Okay. Our periodic table says that the molar mass of antimony is 121.76 grams per mole. And we know that Avogadro's number is 6.022 times 10 to the 23 atoms per mole. Okay, so this is the information that we can use to solve this problem. So we'll start off with our given information. They told us that we have 1.95 times 10 to the 21 SB atoms. Okay, so I want to get rid of atoms and I'm going to turn it into moles because that is the conversion that I can do with Avogadro's number. So atoms goes on the bottom and 1 mole goes up top. So 6.022 times 10 to the 23 atoms. I know that's really small, but you guys know what Avogadro's number is. So even if you can't read it, like, you know what it is. So now our atoms unit will cancel out. Okay, now I'm going to go from moles into grams. So if mole is up here, that unit is going to go onto the bottom of my fraction bar. And I'm going to use the mass value from the periodic table up here, 121.76 grams. Okay, so now my mole unit cancels out. And now I'm going to use this last conversion, which tells me that, well, if I have grams up here, I'm going to put on the bottom. I'm going to put ounce up here. That tells me that every 1 ounce has 28.35 grams. Okay, I keep the number and the unit from my unit equation. I keep them attached when I'm putting them into my dimensional analysis. So I have 1 ounce in my unit equation. So I have 1 ounce in my conversion factor. 28.35 grams, 28.35 grams. Okay, so now I'm going to plug this into my calculator. 1.95 times 10 to the 21 divided by 6.022 times 10 to the 23 multiplied by 121.76 divided by 28.35, because everything that's on the top of the fraction bar, I multiply. Everything that's on the bottom, I'm going to divide. So everyone take a minute to put that in your calculator right now. Okay. And we should end up with 0.0139 ounces as our final answer. Okay. For this next example, we're given the volume and the density of mercury, and we're asked how many atoms are there. Okay, so let's write down this info. Okay. So again, let's think of a roadmap. They told us what the volume of our mercury sample was. right? They told us that we have 12 quarts of mercury. So at this point, if you're looking at this question, you're like, I just don't know what to do with this. Think back to your table that has quarts and ounces and pounds in it, and see what unit your table converts quarts into, right? Your table 1.3 has a way for you to convert quarts into liters, okay? So you can change the volume of 12 quarts into a volume of liters. Once you have a volume in terms of liters, now you can convert it into milliliters. And this is important because your density is in terms of grams per milliliter, okay? And as long as the volume value that you have, that you are attaching to your sample, as long as this volume unit is the same volume unit that's in your density, you'll be able to use your density to convert from volume into mass. So you can go right from milliliters into grams. Once you have a value that's in terms of grams, now you can use the molar mass to convert it into moles, and then you can use Avogadro's number to convert it into atoms. All right? Just talk yourself through this process. 90% of the time, it seems worse than it is. I would even recommend taking a second right now. If you didn't get this roadmap on your own, now that you have it, try to set up the problem before you watch me do it. Okay? So I'm starting here with 12 quarts. And the first thing I'm going to do is look at table 1.3, and I see that there are 1.057 quarts in every 1 liter. I know that my quart unit is going to go on the bottom because it has to cancel out, and liter is going to go up on top. So there are 1.057 quarts in 1 liter. That's 1.057. Okay. I look back at my table, and I see that in every 1 liter, I have 1,000 milliliters. So I can like check off when I've gotten to these parts. Now this conversion here, I'm going to use my density here. Okay. And you're going to use density just like any other unit equation. When you see your density written out like this, 13.6 grams per milliliter, you can rewrite this as 13.6 grams of mercury equals 1 milliliter of mercury. All right. So when you want to convert from milliliters into grams, you can set up your density information as a conversion factor to help you do this. Your milliliters value will go on the bottom because it needs to cancel out, and your grams needs to go on top. And we see we're going to keep the numbers together. So 1 milliliter is going to have 13.6 grams. Okay. Now we're going to convert grams into moles by looking up the molar mass of mercury on the periodic table. Okay, my grams are going to go, my unit of grams will go on the bottom, and then 1 mole will go up top. When I look up mercury on the periodic table, I'm going to write the molar mass of it. I'm going to note it down here for us. The molar mass is 200.59 grams per mole. Okay. So 200.59 grams in 1 mole. So now my unit of grams cancels out. All right. Now to get to atoms, I'm going to use Avogadro's number. And Avogadro's number tells me that in every 1 mole of anything, I have 6.022 times 10 to the 23 of that thing. In this case, I have 1 mole of mercury, which means that I have 6.022 times 10 to the 23 atoms of mercury. Let's erase some of this. Okay, and now I'm going to plug this into my calculator. Okay, and definitely try this. Another long one, so definitely try this. I guess if we were rounding this to the correct number of sig figs, we'd stop it at 4.6. Okay, so for the next one, the next couple that we're going to finish up with, they're kind of weird. Okay, and I made them weird on purpose because I wanted you to just think about how to do these more complex looking conversions. So again, take some time before you watch me do it to actually attempt to set them up on your own. Okay. So we're starting here. We have $1973.99 per pound. We want to convert that into dimes per decigram. Okay, now, I mean, I think we've talked about this before in that earlier video, where when we have a complex or a derived unit like this, where we have 2 different measurements in 1 unit, that you want to rewrite this as a fraction. And I'm going to go as far as to take the symbol and rewrite it in terms of words so that it follows like a familiar format. So I'm going to rewrite this as $1973.99, and that's going to be over 1 pound. Okay. Now I'm going to be focusing on converting this dollars value in terms of dimes and this pounds in terms of decigrams. Okay, so I'm going to start off with dollars. I know that in every $1, I have 10 dimes. Okay, so my unit of dollars cancels out, and I have a unit of dimes up top, which is good. I can leave that there. So now I have to work on converting pounds into decigrams. I have pounds in the bottom of my fraction bar here in the information that I was given. So it needs to go up top of my conversion so it cancels out. And in table 1.3, the conversion that I have that has pounds in it, well, the more useful of the two is going to be the one that includes the unit of grams. So for every 1 pound, I have 453.59 grams. Okay, and I say that this is the more useful of the two because grams, remember, is a base unit. It has no prefix. So once I have this value in terms of grams, in my next step, I can convert grams into decigrams, or G, right? Because grams would just be G into DG. And if I look back at my metric prefixes, if you look up the term deci, it's 10 to the negative 1. So every 1 decigram is going to be 10 to the negative 1 grams. Okay, so if I look at how my units cancel out, what I'm left with at the end of this is dimes on the top and decigrams on the bottom. So we'll have 1973.99 times 10 times 10 to the negative 1 divided by 453.59. Okay, and we end up with 4.3519 dimes per decigram. And when I'm counting my significant figures in this example, you're going to see a few things. One, that 2 of my conversions are definitions, so they are exact numbers. Okay, and exact values have an unlimited number of significant figures. So my final answer is not going to be limited by either this conversion factor or this one, because the definition of a dollar is that it has 10 dimes in it. The definition of a decigram is that it's 10 to the negative 1 grams. Okay, these values are measured values. Okay, so when I have my conversion here that says 1 pound is 453.59 grams, this last decimal place was estimated. That makes it a measured value. That means that my final answer has to be limited to the 5 significant figures that are in this measurement, in that conversion factor. Okay, let's try this one. Again, try to set it up before I do. Okay, so I have my first step here, 88.7 ounces per 1 cubic foot. My ounces I'm going to convert into milligrams. My cubic feet I'm going to convert into microliters. Okay, so my first step, I'm going to use a conversion that gets me out of ounces and into grams. Okay, so every one ounce is going to be 28.35 grams. So we see that cancels out. And now I'm going to go from grams into milligrams. So every 1 milligram is going to be 10 to the negative 3 grams. Okay, so now this unit checks out. That's where we want it to be. So now we're going to work on cubic feet to microliters. And this is one where you might be like, why? Right? But you just have to go step by step here. You can look back at your table 1.3, and the 1 unit in here that includes feet in it is the conversion between feet and centimeters. You also know a conversion between feet and inches by heart, probably. But the feet to centimeters one will be helpful here. Okay, if we can convert from feet into centimeters. Then we're going to be able to cube these units. So we'll have cubic feet and cubic centimeters. Once we have cubic centimeters, we can convert that into liters. Once we have liters, we can convert that into microliters. All right, and that's going to be the format that we want to follow here. So before we can get to cubing our units like I did here though, we're going to write out the exact unit that they give us in our textbook, the exact conversion that they give us in our textbook. Feet is on the bottom of my given information, so I'm going to put it up top. And I'll put centimeters on the bottom. And I want to fill in the numbers from my conversion. So my conversion from my table 1.3 says that 1 foot has 30.48 centimeters. Okay, once I fill this in, now I'm going to cube this entire thing. Okay, I'm going to remember to cube the numbers that are inside of it as well. You can't forget to cube those numbers. So when you write this out, what this fraction, what you're really doing in here is 1 cubed times foot cubed over 30.48 cubed centimeters cubed. Okay, you have to remember to cube these numbers in here, or else you're going to end up with a value that doesn't match. And we can actually do that. I'm going to actually cube this number separately. I'm going to fill it in here. Okay. It's a big number, but I think it'll be good to do that. So when I cube this unit, and everyone here, I mean, you're watching this video, so you know that I'm cubing this unit, and that's what I'm rewriting here. So 1 cubed foot cubed, what does that come out to? It comes out to 1 cubic foot. Okay, when I do 30.48 cubed, I get 28317 cubic centimeters. Okay, but you see now my cubic feet, now they can cancel out because now the units match up. Once I have this unit in terms of cubic centimeters, I can look back at my table and it tells me that now cubic centimeters has to one top and liters goes on the bottom. And every liter, there are 1,000 cubic centimeters, right? And now I can look at my metric prefixes and I can convert from liters into microliters. And remember, that's what that weird looking U is. It's a micro. So every 1 microliter has 10 to the negative 6 liters. Okay, so with all that craziness filled in, cancel out these last units. Okay, we end up with 0.0888 milligrams per microliter. And if that's not the answer you got, do try to plug everything back into your calculator. This step right here is definitely one where I see people make an error with the cubing that can affect your final answer. Okay, I have one more example for this video. And that's going to be this conversion here. We're going to convert from 22.50 gallons per minute into gigaliters per century. This is such an obnoxious conversion. But it's good practice. So the first thing I'm going to do is rewrite it. So 22.50 gallons per 1 minute. Okay, and I'm going to go from my first step. I just like to start with whatever unit is on top. As you've seen multiple times, that's just my method to approach these. So I'm going to look at my table. I'm going to convert gallons into liters. And then I'm going to convert liters into gigaliters. Okay, so according to my table, every 1 gallon is going to be 3.785 liters. Okay, and then I can look at my metric table. The prefix giga is 10 to the 9. And every 1 gigaliter, there's going to be 10 to the 9 liters. So gallons has canceled out, liters has canceled out, and now I'm in terms of gigaliters, which is where I want to be. Okay, so now I'm going to go from minutes into centuries. So minutes on the bottom of my given information means that it has to go on the top of my conversion factor. If you know the shorter version of these time conversions, you can use that. I'm going to go through it very step by step. So I'm going to go from minutes to hours. Then I'm going to go from hours to days. Days to years. And then years to centuries. Okay, so I start here. I know that in every 1 hour, there are 60 minutes. So now my minutes have canceled out. I know that in every 1 day, there are 24 hours. So now my hours have canceled out. I know that in every 1 year, I have 365 days. So now my days have canceled out. I know that in every 1 century, I have 100 years. So now my years have canceled out. Okay, so I have 22.50 times 3.785 divided by 10 to the 9 times 60 times 24 times 365 times 100. Like I said, it's obnoxious, but you know, what are you gonna do? Okay, and we're going to end up with 4.5 gigaliters per century. I got 4.476, but I'm going to, I mean, there's not exactly 24 hours in a day. It's like give or take. So I'm going to limit my report to 2 significant figures because of that value here. Okay. So that's the last set of examples. If I have time, I might put up one more kind of chapter 1/2 set of review slides, but I don't know how much time we'll have before the next exam. If it happens, awesome. If it doesn't, this is more than enough for you to review with, I hope. Let me know, let any of us know if you have any questions about any of these calculations so we can clear it up.